Hello, welcome, welcome. I'm not able to get the person view working at all today, so I don't know about that. So we're just going to go right to the paper view, and we're going to be looking at surface area. It's not that tricky. It's not that hard. It's just something that is pretty straightforward, actually. The formula for the area of the surface for an equation. So this is you're looking at, we have one of these surfaces. So we have one of these surfaces, you know how we have them, and we're just looking at finding an area of the surface area, and um, and so the formula, they go over the formula in the book a little bit, hand wave it a little bit, but I'm just going to give you the formula and we're going to practice it. It's the partial of x squared, the square root, the double integral, the square root of 1 plus the partial of x squared and the partial of y squared over whatever domain, whatever area from the bottom up that you're going on. Anyway, so in order to apply this, to use this, this plane right here, this is example one. Find the R. Darn it! I thought I fixed every typo on this. Typo. Find the area of the surface. The part of the plane 6x plus 4y plus 2z equals 1 that lies inside the cylinder x squared plus y squared equals 25. So right here, they're talking about the domain. So over our region that we're talking about, that's what they're giving us right here. And right here, we just need to solve this for z. So that's going to be our first thing to do, is to solve that for z. So if we solve for z, and I get 2z equals 1 minus 6x minus 4y. And then dividing by 2, I get z equals half minus 3x minus 2y. And then if I take the partial of x, that's fx here. If I take the partial of x, I get negative 3. And if I take the partial of y, I get negative 2. And so I'm kind of making my plan of how I'm going to put stuff in. So this is going to be negative 3 squared and negative 2 squared. And in order to find out my dA, remember dA is either going to be dx dy or dy dx. Or if it's better, you can go in and do it in polar coordinates. And so I have this x squared plus y squared. X squared plus y squared equals 25. And so it's on this cylinder that we're trying to, the cylinder that's going up and hitting our plane, and that we're trying to find our surface area. Because this is a circle, it is much better for us if we do it in polar. And so I remember that x squared plus y squared equals r squared equals 25. So r equals 5. And so that's the equation of that circle right there. And our bounds that we're going to run for r are going to go from 0 out to 5. And so for r, we're going to have the bounds 0 to 5. And I'm going all the way around the circle. For theta, I'm going to have 0 to 2 pi. And so now I think I'm ready to put this together. Let's see, the area of the surface, our little formula, is the double integral. In this case, I'm going to be using r, and I'm doing polar because it would have been difficult to do it in rectangular coordinates with a circle. And so remember that you put r on the inside, so r is going from 0 to 5. Don't get a choice on that. And theta is going from 0 to 2 pi. Theta is going from 0 to 2 pi. And my integrand is the square root of because it's surface area, 1 plus negative 3 squared plus negative 2 squared. And then remember when you change dx, dy, or dy, dx, either one, when you change them into r and theta, it's r dr d theta, right? So this is going to be r dr d theta. So when the dust clears underneath here, 1 plus the square root there, that's 9, and 4 and 1 is the square root of 14. So I'm getting for my area of the surface going from 0 to 2 pi, from 0 to 5, and this is the square root of 14 r dr d theta. And the first thing I'm going to do is I'm going to take this integral right there, and I like to circle it, and that's just in terms of r. So that's going to be r squared over 2. So the square root of 14 is just a constant, so it just stays there, r squared over 2, from 0 to 5. So upper bound minus lower bound, the lower bound is 0. And so when we put that in, we're going to get 0. So this is going to be 5 squared, so that's 25, square root of 14 over 2 minus 0. So just to kind of reiterate what we have here, we're now on 0 to 2 pi. And we have here 25 square root of 14 over 2 d theta. And that's a constant. So when we integrate a constant, we just get theta. So this is 25. It seems so much harder when I was doing it before. But theta here, and from 0 to 2 pi. And so when we do up bound minus low bound here, so 0. So this is 25 square root of 14 over 2 times 2 pi. And we got 0 on the other. And so the 2's cancel out, and I end up with my area of the surface being 25 square root of 14 pi. Because the 2's canceled, and then that's what I have. So I did a lovely job on that. And it kills me that I had I make that typo on area and r all the time. It drives me nuts that I do that. And so anyway, I've got a note in to fix it. And so we're going to look at our next example here, example 2. It says, find the area of the surface, the part of the sphere, x squared plus y squared plus z squared equals 4, that lies above the plane z equals 1. And so that's what we're trying for. So the first thing I have to do, so there's 2 things I'm going to have to do. I have to figure out what, I have to take this and solve for z so that I can find my partials of x and my partials of z, and partials of x and partials of y. And then in order to find my domain that I'm going to be integrating over, I have to let z, I have to solve these, put them together, 2 equations, 2 unknowns form. This one's already solved for z, so plugging in z is all that I have to do. So I kind of have those 2 things that I have to do. And so one is to find the domain that I'm on, and the other is to find the integral that I'm going to be integrating over. And so I need to solve for z here. So this is going to be z squared equals 4 minus x squared minus y squared. And then I'm going to take the square root of that, and oh, it's Tyler. Hi, Tyler. I'm making a video. Can I call you right back?
Oh, sorry. Yeah.
No problem. We'll watch the game together.
Okay.
Okay, bye. Okay. So, so when I take the square root, z equals plus or minus the square root of 4 minus x squared minus y squared. And most of the time, we're looking at ourselves being um, in, they want above that lies, let's see, the part of the sphere that lies above the plane z equals 1. So if we're going above the plane z equals 1, then that means that we would be looking at the part that's positive, right? So this would be z equals the square root of 4 minus x squared minus y squared. So if I take the partial of x, then what I'm going to get there is, let's see, that's going to be 1 over 2 the square root of 4 minus x squared minus y squared multiplied by the derivative with respect to x. So the derivative of 4 is 0. The derivative of negative x squared is negative 2x. Remember, y is being treated as a constant, so that's also 0. And the 2's cancel out here. So our partial with respect to x is negative x over the square root of 4 minus x squared minus y squared. And likewise, the partial of y is equal to negative y over the square root of, there's symmetry there, right, that I can kind of take advantage of. And so there is my, ouch, oh, I split my toe. Ooh, that really hurt. And so there's my partial of x and my partial of y. And so those are what I need for my formula. When I put these together, so I'm going to be plugging those nasty looking things in that formula, squaring them, right? Adding 1, putting it over the square root over the top of it. Now I want to find the region that I'm going to be integrating over, and I've got to put these two things together. It's where they intersect, is where I'll be interested in. So that'll be x squared plus y squared plus 1 squared equals 4. So I'm plugging in z equals 1 into this other equation. So I get x squared plus y squared equals 3. And so that tells me that's the region. And then when I draw this, of course, it's circular. It's got a radius of the square root of 3, right? And so I know that I'm going to be, instead of using dx and dy, I'm going to be using polars. And I kind of like to change things, on this. I was noticing that, I mean, if I change this all into polar right now and then squared it, well, I should get the same answer. Squared each piece and add 1 and all of that. I should get the same answer. But I thought that, well, maybe it's better to first put this in. So this is SA, and this is going to be the double integral, and this is over D, they would say, over the domain. And I'll work on that in just a second. But this is going to be the square root of 1 plus, and then this one, that squared. And I thought that it was going to be really nasty, and it actually is not as bad as I was going to say that it was. Right, and this is DA. And I'll get some. I'll get the. After I fix this up, then I'll put all those other things on there. And so I'm just waiting on that just a little bit. But when I square this and I square a square root, I just get that radicand back. So this ends up being, so I'm going to have this double integral, and I'm going to have here 1 plus x squared over 4 minus x squared minus y squared plus y squared over 4 minus x squared minus y squared dA. And that's where you can see that it's kind of nice that I went ahead and got a common denominator with the 4 minus x squared minus y squared. And then I started plugging in my polar, because I'm going to go to polar. And so because my circular, because I have the circle that I'm integrating over again, and they're not all polar. I happened to pick two polar ones, but I was trying to pick one where you had to set these equal. And so I couldn't find one of those that wasn't polar. And then I'd already done that other example. So I was kind of like, um, anyway, it's good practice for us to do the polar, I think. So I got a common denominator here. This is 4 over that. And that turned out, I thought, just as good as any. 4 minus x squared minus y squared plus x squared plus y squared, all underneath the square root, and all over 4 minus x squared minus y squared dA. And so see how that the x squared and the minus x squared and the plus x squared just all went away, just kind of coincidentally. I didn't really think, oh, that I would make that happen, but it sort of just happened, and it was kind of lovely. And so because I was thinking I was going to have a bunch of x squareds and y squares all in the numerator and the denominator, and every time you have an x squared y squared combination, you're having an r squared. So so in the numerator I have the square root of 4, which is 2, and in the denominator, so in the numerator I have 2, and in the denominator I'm having 4 minus x squared minus y squared, and this is where I'm going to go to polar. And so, and you could have already gone to polar already. So 4 minus r squared. And my bounds for r are going out from 0 to the square root of 3. So 0 to the square root of 3. This is for r. And my theta is going from 0 to 2 pi. And r dr d theta. And so now it's just a matter of integrating that, and I'll have then found the area of the surface, and so that's all I've got left, and I'm going to do a u substitution to integrate this part right here. So this is the part I'm doing right now. Whoops, I almost encircled that. And my u substitution, u equals 4 minus r squared, du equals negative 2r dr. The bounds, the lower bound is r equals 0, so u equals 4 minus 0 squared, which is 4. And the upper bound is r equals the square root of 3. So u equals 4 minus the square root of 3 squared, which is 1. And the bounds are not in order, and they don't have to be. And some people are like, well, put them in order by doing the -1 thing. And I'm like, oh, I don't, it doesn't bother me that they're not in order. And so I just go ahead and go with it. And so what we're going to get here, I'm just trying to integrate this part that I've got a box around, and then I'll pick up the other part. And so my bounds are going to go from u is 4 to u is 1. And I have 2r over the square root of u. And then I have du. And I like to write this as, this is du divided by negative 2r equals dr. So that I'm replacing, I put the r up here, right? You saw that already. And I'm replacing this with over negative 2r. So the negative comes out in the front, and I get the negative, and I'm going from 4 to 1. If you're saying that, hey, you could go from 1 to 4 and get rid of that negative, you're right. I definitely could. Do you think it's worth it for me to do that? And the 2r cancels, and the 2r cancels. I don't hear any of you saying anything, so I'll just say that you said that it would be a good idea to change it, make that a positive, and then change it from 1 to 4. And so this is going to be u to the negative 1/2 du from u equals 1 to u equals 4. and adding 1, integrating that. And so I'm still in this, I'm integrating this part right here. I also had this u substitution part. I ought to be able to do it in that amount of room. And so this is going to be, when I integrate that, u to the half divided by half, which is the same as multiplying by 2. And my bounds are 1 to 4. So this is 2 times, and then 4 to the half minus 1 to the half. And 4 to the half is 2 minus 1. So this is just 2 times 1, which is 2. And I'm not all done yet, but now I'm almost done, right? And so so our surface area equals, I'm just resetting the integral from theta to 0, and theta is 0 to 2 pi. So I'm coming right here, and I'm picking up, I circled what I was integrating, and so I'm just picking back up where I was. I integrated that, I got 2. So this is 2 d theta. And so this is 2 theta from 0 to 2 pi. And so this is 2 times 2 pi minus 2 times 0. And so that's 4 pi. And oh, shoot. Darn it. Darn it, darn it, darn it. I'll hold it there. I'm sorry. Because of me not being able to set up the screen right, I didn't have my thing where I could see what I was writing. And so until I looked over there. And so there we have the how to do the surface area. So short lesson, very short lesson, and not too bad. Not all of them are polar, so go try some of the homework ones, you'll see. And but these two were, and I'll catch you in the next video. Okay, bye-bye.